So continue on for part 2. Rinse the pipette with deionized water. You're also going to want to rinse the pipette with the iodine solution. Next, you're going to fill the pipette with iodine solution. Using a pipette filler. Okay. Take in liquid until the bottom of the meniscus is at the graduation mark. Then you want to touch the end of the pipette against the side of the beaker, because that gets rid of any excess iodine that might be hanging outside of the edge of the pipette to ensure an accurate result. Then you're going to transfer the solution to the conical flask that you're going to use in the titration. And again, you're just going to use that same sentence up here. Touch the edge of the pipette against the side of the conical flask this time. So instead of there, we're going to say instead the side of the conical flask here. And that's it. So that is B. Now C, if you want to give a go to C, name a suitable indicator for this titration. At what stage is the indicator added, and state the colour change. Okay, so this is what I would write for that question. The suitable indicator is the starch solution. The stage in which the indicator is added is when the liquid in the conical flask is a pale yellow, which means it's very close to the end point of the titration. And the colour change that happens is the blue-black. The blue-black is picking up that there's still iodine present. And then the change is colourless when the iodine is disappeared from the actual conical flask and all has reacted. Now, if you're asked why is the starch added in so late, the answer is this. So iodine is absorbed into the starch indicator. So we want to actually leave off adding the starch indicator as much as possible so we can avoid the iodine being absorbed into it. If we were to add it in earlier, it might throw off our endpoint result, so it would give an error in the end average titer. Okay? Now we're going to go for D. Now this is our maths question. Okay, D, the number of moles of iodine in each 25 centimeters cube portion. So we have one piece of information about the iodine here, which is 6.35 grams was in 500 centimeters cubed. So when we're dealing with number of moles, concentration, it's always in liters. So if I just multiply that whole thing times 2, I'm going to be able to just convert that to, if I made up the iodine to a litre of solution, which is going to be 12.7 grams in 1 litre. So now it should be easy enough to convert straight from grams into moles using this formula. Number of moles equals mass over relative molecular mass. So I have the 12.7. The relative molecular mass of iodine is 254. Put that into the calculator and you're going to get 0.05 moles per litre. for the iodine solution. So the question is not asking how many moles are in a litre, it's asking how many moles are in each 25 centimetre cube portion. So I want to see how many 25 centimetres cube portions is in a litre, and we'll get 40. So that means if I divide this number by 40, I will find out how many moles are in each 25 centimetre cubed portion. And there's your answer for part 1 there. Now part 2. The number of moles of sodium thiosulfate required to reduce this quantity, so it's still talking about the 25 centimetres cubed of iodine. And again, our answer for that was in each 25 centimetres cubed portion of iodine, we have 0.00125 moles. So if we look at our chemical equation, we have 0.00125 moles. We need to figure out how many moles of sodium thiosulfate will react with that many moles of iodine. And if we take the two reactants, we can see that 1 mole of iodine will react with 2 moles of sodium thiosulfate. So 0.00125 moles of iodine will react with 2 times that, because you can see it's a 1:2 ratio here. So all we have to do is multiply this number by 2 to find out how many moles of sodium thiosulfate will react with that. And once we multiply that by 2, we get 0.0025 moles of sodium thiosulfate for part 2. Okay, part 3, the concentration of the sodium thiosulfate. So we should have enough information to use this trusty formula here, which relates our oxidizing agent with our reducing agent using the molarity, the volume, and the number of moles. So our oxidizing agent is the iodine, so we're going to go for the molarity of the iodine. You remember, when we're using this formula, we input the iodine concentration in moles per litre. So you're going to use that original 0.05. The volume of the oxidizing agent used is 25 centimetres cubed. And the number for the oxidizing agent is 1, because that's the number here, the imaginary number in front of iodine. Then we don't know the molarity of the reducing agent. The volume of the reducing agent is here given in this question part here, the average titer, 17.85 centimetres cubed. And the number for the reducing agent is 2. As we can see, 2 is in our chemical equation there. So if we put in all these values, and if we maneuver the equation around to just find the molarity of the reducing agent, we should find it to be 0.14 moles per litre of sodium thiosulfate. Okay, that's the concentration done. And then the last one is just to convert from moles per litre to grams per litre. This relative molecular mass here is 248. And we've worked that out in part 1 of the video. And you can just work it out again if you want, by going to your periodic table and adding up all the relative atomic masses of these elements. Anyways, they come together to be 248. So using our formula here, number of moles equals mass over relative molecular mass. We have the number of moles, the concentration. We need to find the mass, and the relative molecular mass is 248. So the mass of the sodium thiosulfate in a litre solution is going to be 34.72 grams per litre. The last question then is E. Explain why the use of distilled water instead of deionized water throughout this experiment would be likely to ensure a more accurate result. So deionized water only has the ions removed. That's part one. And the second part is it could still contain non-ionic substances, whereas distilled water doesn't contain any extra substances. It's just pure H2O. Okay, and that is that question all fully answered.